You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Amir Siraj. Amir studies astrophysics at Harvard University and is interested broadly in theoretical astrophysics. He is a Goldwater Scholar and US Presidential Scholar. He is co-president of Harvard Students for the Exploration and Development of Space and former senior US editor of the Harvard Political Review. His research advisor is Professor Avi Loeb.
Amir Siraj, welcome back to the program.
Thanks for having me, John.
Amir, the words jet lag do not quite apply to what you did in globe crossing in order to get to the Silver Star to join Dr. Loeb on the expedition for finding IM-1. What was that like? 50 hours straight of travel.
It was insane. I was actually officiating my sister's wedding in the English countryside, and it ended at about midnight. And then at 4 a.m., I took a car to Heathrow, flew Heathrow to Singapore, then maybe 6-hour layover, Singapore to Manila, 9-hour layover there, Manila to Port Moresby. And the layover in Port Moresby was longer than expected, almost didn't catch my flight to Manus Island because there was an issue with the weight of my carry-on. So during that, right before that last leg, I was very, very nervous. But I finally made it to the island and then to the boat. And getting to the boat after 52 hours of travel was it was a surreal moment because I had been dreaming of combing the ocean floor for fragments of IM-1 for years at that point. And I think that combined with the sleep deprivation made it really feel like a hallucination. But it was real, and it was one of the most exciting weeks of my life.
Now, constraining the potential location, the path to where IM-1 fell was Manus Island, a seismic station there. What did that feel like when you actually set foot on that island where you had been spending so much time trying to constrain down the fall area of IM-1?
It was surreal. You know, I had I'd read so much about Manus Island and about the oceans in that area of the world and the weather patterns and all of this information on paper because, as you mentioned, the location as provided by the U.S. government for the fireball of IM-1 was only given to 1 decimal point in precision in terms of latitude and longitude. And so that corresponded to about 120 square kilometers. So that's a pretty large search region. And for a 2-week survey with a sled that's 1 meter by 3 meters, that's a very, very difficult task. That's why over the past half year or so, I have really focused on how to narrow down the search area. And so that involved combing through seismic data. Basically, the idea is that earthquakes cause acoustic tremors that are picked up by seismometers, but so do fireballs from meteors. And we were very lucky. The nearest landmass, Manus Island, to the fireball, actually had a seismic station on it, and the data was publicly available. So this was a huge win. There were also many other seismometers that seemed to have picked up IM-1, but only one other very clear signal, and that was from the tip of Australia. And so using those seismic signals, I was able to also incorporate the weather at that particular time, including to essentially calculate sound speed as a function of altitude in the atmosphere. So with that profile, I was able to time when the pulse should have arrived to the seismometer. And also I fit the reflections that we would expect from sound traveling from the fireball to the water and then to the seismometer. Using these techniques, I was able to determine which strip within the Department of Defense's search area was the most likely region. And so as a result, we had a much sort of easier time because we only had to survey in depth about 16 square kilometers rather than 120 square kilometers. Basically, in the lead up to the expedition, I was focusing all of my efforts on this localization problem, and Avi was focusing his efforts primarily in terms of funding and procuring a donor who would support the vision for the project and have the financial resources to back it, and also figuring out where we would get this boat from, which ocean experts and deep sea exploration experts would accompany us on this journey, how would we get the sled manufactured, all of those very complex logistics. And to see it finally come together and to see the waters that I had stared at on a map for years and years, it was a mind-boggling experience. And just the process of putting those two together, the experiences of actually being on the boat, being there, and the years of research that I've put into this, that's taken a lot of time, and I think that's a process that's going to continue because it was absolutely surreal.
Astronomy on the ocean floor. Now, when you went in and decided, I'm going to go to college and become an astrophysicist, did you ever think that you would end up on an island in Papua New Guinea looking for an interstellar meteor? Or did you really expect that it would just be all equations and teaching?
Yeah, well, I can't say that I expected this. And it's so funny because, as you know, this dates back to 2019, and that's when I found in a publicly accessible database. I mean, at the time, I'd been collaborating with Avi Loeb on understanding Oumuamua, and of course, that was the first interstellar object discovered passing through the solar system. Interstellar objects carry a wealth of new information about our cosmic context, and so me and Avi were eager for a sample size larger than one, and meteors, small space rocks that collide with the Earth, were the perfect place to search. Avi basically proposed that with this government catalog, we could maybe come up with probabilities of interstellar origins by checking how far the solar system's plane, how far out of the plane each meteor's velocity vector pointed. But soon afterwards, I realized that I could actually run time backwards in a gravitational simulation to chart out the precise trajectories for each meteor and check whether each was bound to the sun or if they were interstellar in origin. Within hours, I made the shocking discovery that a fireball within the database was interstellar. And of course, I didn't believe it. It was such an extraordinary result that I rechecked my calculations dozens of times. And it was just so ridiculous of a notion because scientists had been searching for an interstellar meteor for at least 7 decades. And here I was a sophomore in college sitting in my dorm room thinking, surely this was too good to be true. And of course, there turned out to be a catch, but it had nothing to do with my calculations. Because the data came from spy satellites, the US government didn't publish how precise the measurements were, and without knowing the level of precision, we weren't sure, we didn't know for sure if it was interstellar or not. And so during that 3-year period, I was dreaming of searching the ocean floor for fragments of IM1. I was still a pure theorist working on the computer or the blackboard or my notebook, but I was dreaming of this adventure. I had no expectations for it to actually come true, but because it was unclear whether we would ever receive confirmation from the US government or not. And while waiting for confirmation, I reached out to the only team that had ever retrieved meteoritic fragments from an observed meteor fall in the seafloor to learn more about it. Now, for context, spherules have been retrieved from the oceans since the late 1800s, but it was only in 2018 that a team involving Mark Fries from NASA retrieved meteoritic material from a specific observed meteor. It was pointed out to me that the mile-deep water at the IM1 site would be a great advantage because it meant that the fragments on the seafloor were unlikely to be perturbed. And so once confirmation of the data arrived on DoD letterhead, I told Avi that I wanted to do this, and I then started my search for seismometer data, and then Avi's search for funding and a boat and coordination and logistics and figuring out how we would get the sled and all of the heavy machinery involved. because this was a seemingly impossible task, right? Looking for tiny pieces of the first interstellar meteor on the bottom of the ocean. Much harder than looking for a needle in a haystack, but it was something that I really believed in and thought it would be worth a shot, because the alternative is actually 1,000 times more expensive, and I've written a paper on it. Sending a spacecraft to a nearby interstellar object is actually a much bigger undertaking. So I thought, why not try?
Much bigger, but perhaps closer now within reach because of the success of this mission. The apple seed produced fruit in this case. But before we get to that, establishing controls with the sled. You set up this magnetic sled with the neodymium magnets, and the first thing that Dr. Loeb did that I saw was dredge an area that wasn't in the search zone to see what you come up with. What exactly did you find in the control areas other than volcanic dust?
So, well, I guess let me start with the big picture, which was in the sort of week. The expedition was about 2 weeks long, and I joined in the second week. And when I boarded the Silver Star about halfway through, and at that point, the expedition team had already found various pieces of human-made debris. And so that included wires and some steel shavings, but the search hadn't yet yielded potential interstellar material. Of course, that wasn't surprising, because this is like trying to find a needle in the world's most unforgiving haystack. And the other point is that the search up until then had largely been motivated by trying to find quote-unquote big fragments. Now, when I say big, I don't really mean big fragments, I just mean ones that are millimeter size or larger, because basically that's the threshold where it becomes very difficult to see things with the naked eye below that. And so millimeter size fragments are much easier to spot than sub-millimeter size ones, and also they carry more mass, and so more mass is better for the ease of analyzing them. But when I boarded the boat after 52 hours of travel, I basically reminded the team that in order to be successful, we needed to be focusing on smaller fragments, ones that were not necessarily visible to the naked eye. And because, of course, the smaller pieces, the greater the abundance and the higher the chance of finding a fragment. My point was that the tiny drops of molten metal that cool into spheres from IM-1's explosion, those should be in the size range of 10 to 700 microns. So decidedly sub-millimeter, and those are the sizes of spherules found from other metallic meteors. And so if we wanted to find materials smaller would be better. And within 2 hours, we had recovered one such spherule. And that was a few hundred microns in size. And then we kept looking with our rudimentary microscopes for in this size range, and we found 50, the majority of which were found by Ryan Weed. This was immensely exciting because it meant that we had found likely meteoritic material. Of course, it could also be anthropogenically produced. Spherules could also be anthropogenically produced, but they are known for coming from meteors, and this meant that we could go test them in the laboratory to see what they were made of. And we already had some initial reads on composition, but really to see whether they were interstellar or not, we would have to check the isotopes. But we'll talk about that later, I'm sure. And during that process, in that second week, once we had established that we could find material that wasn't obviously human-made and that could potentially be interstellar, we did control runs very far away, a couple of control runs very far away from the search area. And we also did ones that were within the search area, but within the DoD search area, but not within the strip that I had calculated. And we did find spherules in the controls, but it seems like there were fewer spherules in the controls than along the strip that I calculated. Now, of course, we were simply looking with tweezers and rudimentary microscopes on the boat for these spherules. And so these are small number statistics, and there were lots of uncertainties involved, including how much time the sled actually spent on the bottom of the ocean for each run and other considerations. So the real test of the control areas will be what we're currently doing, which is combing through the samples for more spherules and perhaps even unmelted fragments. And the idea is that once we are able to find many more and increase the number of spherules and put every run on an equal playing field, then we will really be able to establish the statistics of what the control regions look like versus the strip. But as of now, from the 50, the plurality come from the strip that I calculated from the seismic data.
Now, the elephant in the room, as far as depositing metal on the ocean floor in this area, is World War II. Did you find any obvious artifacts that were related to the war that would give you something to compare to as far as metals recovered to that event where, I mean, who knows what would have happened in an area like this during the war?
Right. Well, we did find shavings of shock-resistant steel, and this could be from normal boat operations in terms of if one were, for example, shaving a tool, but it could also potentially be from military activities. It's hard to tell. There were also manganese platinum wires. Let's put it this way. It was clear that there was a lot of human-made debris, but it would be much more difficult to tell whether that came from World War II or not. Now, in the lab, we should get fine-grained detail on the radioactive isotopes in the fragments that we found, both the spherules and the larger, likely human-made debris. That might be very instructive in terms of seeing if we have higher than expected levels of radioactive isotopes.
Now, isotopes are going to be very important here. In this case, of course, with pre-war nuclear testing, iron, steel changed. It became contaminated after the detonation of the first atomic bomb. So you'll be able to tell not only if you have a piece of steel from a Mitsubishi Zero or something like that from 1944, you'll be able to tell if this piece of metal was from either before this date or after that date. So you can at least characterize the false ones as far as whatever you find. But these spherules that you found later within the search zone are weird, as far as I can tell, and don't really correspond to materials that you would expect to see from just normal shipping and machine shops on battleships and things like that. This is weird stuff. This is molten metal, or formerly molten metal, that is layered. Now, give us a profile of the spherules that were found within the search zone that led you to believe that, yes, this might be part of IM-1.
Yeah, so these spherules were primarily made of iron, about 85% iron, roughly, and they contained very low amounts of nickel. And that's something that is unusual, but not unheard of for meteoritic fragments. To put it in context, about 5% of metallic spherules found on the ocean floor have very low nickel content. Very low, I mean below 1%. And that basically corresponds to what we were finding. And so it is unusual. Nickel also undergoes isotopic fractionation at a quicker rate than iron. So it's possible that if you have a meteor coming in at a high speed, you could reduce the nickel content relative to the iron content. That's one thing that's interesting. And they also contained several other metals, small amounts of chromium, a few percent magnesium, small amounts of titanium. And so these, I would say the bulk of the spherules are likely meteoritic and potentially part of IM-1. The only way to tell if they're part of IM-1 or not is through the isotopes. And we weren't able to measure the isotopes with the machinery we had on board. Now, right when we landed back in the US, we headed to the nuclear engineering lab at Berkeley, and we started this isotope analysis. And now that we're back in Cambridge, we're continuing this analysis under the supervision of Stein Jacobson, formidable scientist. He's a professor in the Earth and Planetary Sciences department at Harvard, and he has a lot of experience dealing with meteoritic fragments and even spherules specifically. And on the plane back over the Pacific, I came up with two tests that I think will be key in determining whether these spherules are truly interstellar or not. And those are tests involving the iron isotope ratios and the chromium isotope ratios. It turns out that having looked at the literature and looked at previous isotope analyses of metallic spherules from the seafloor, from meteors in the solar system, there are very, very tight ranges for the ratios of different iron isotopes and for the ratios of different chromium isotopes. Now, various corrections have to be applied for isotopic fractionation, which is when lighter isotopes basically evaporate faster in the atmosphere relative to heavier isotopes, and so that ends up changing the ratios from the unmelted body outside of the Earth's atmosphere. But after taking all of that into account, there seems to be a pretty tight range in terms of the flavors of iron relative to each other and the flavors of chromium relative to each other. And so these isotope ratios are fairly well established for solar system meteors. And once we get the measurements for the spherules that we found, I can very easily calculate these ratios accounting for isotopic fractionation and then compare them. And we can check how weird they are relative to background solar system meteors or not. Now, obviously, interstellar material would not necessarily have the same exact blend of isotopes of iron and chromium as we have in the solar system, so that would be a telltale sign if we got highly anomalous results relative to the literature.
Now, what about other isotopes outside of that range? So say you look at these spherules and you start seeing that they're all very similar and they all appear to come from the same main mass, the IM1 entering the atmosphere. Now, can you establish a date range? In other words, how old is this object? How long has it been wandering the galaxy before it fell here? In other words, can you look at isotopes like aluminum-26 or something like that and say, well, that's missing here, that should be there for a meteoric object, so this must be very ancient, much older than the solar system. Now, can you go that far?
I think we will be able to. We already have some preliminary reads that tells us that we can measure uranium, we can measure thorium, we can measure various isotopes of lead. And so typically with uranium and lead, you can do what's called uranium-lead dating. You can also do that with thorium, which decays into a different isotope of lead. Of course, that technique relies on all of the lead being radiogenic. So we're in the process of figuring out whether that kind of dating can be applied to the sample or not. But certainly the precision of the instruments we have available to us are of the highest caliber. So we will be able to look into any radioactive isotopes that might be there. So we'll be pursuing all avenues of inquiry, including aluminum-26, and doing the best job that we can with the data that we have. We're really lucky that it'll be pretty cut and dry from the data, and it's less about building narratives. You know, I get to build narratives at the keyboard when I'm making music, but when it comes to science, it's all about the data. And we're really grateful for the help of Stein Jacobson from Harvard, because he is a world expert in terms of isotopic analysis of meteoritic fragments.
Now, melting. One thing that seems very clear from a preliminary basis, from what I know anyway, is that these are melted spherules, and they look like what you would expect from something stripping off a meteorite entering the atmosphere. And they're layered and merged. So you see this clear indication of melting. So this isn't just something that you would find from, a mundane source. This is something that underwent very clear heating and really does look meteoritic in nature. Would you agree with that assessment, at least at this stage preliminarily?
Yes, I would say the majority of these spherules, I would say the vast majority look like they've undergone really large amounts of heating, and the majority of them seem meteoritic in origin. We can even see that, there are many ways to see the effects of exposure to high temperature. One is the fact that we see some spherules that look like composites of many. So spherules that joined in midair and then cooled quickly. We also see when we cut into a couple of spherules, we saw internal structure, meaning inclusions of metal, that basically tiny spherules coming together to make a larger spherule. And in that process, you have different metals cooling at different rates, different spherules cooling at different rates. And so you kind of get these inclusions. It's not completely homogeneous inside. You also have dendritic structure on the surfaces of many of these spherules, which are hallmarks of meteoritic origin. So, yes, absolutely. The real question is, are these interstellar? And since spherules are found all over the ocean floor, the good news is that isotopes will be definitive in terms of telling us the origin and how weird the isotopic ratios are relative to the solar system.
I think the indications already are that this is weird stuff, and it's not necessarily unnatural or anything like that, but just weird stuff. If you were to find a meteorite main mass with showing some of these elements that were at least initially detected on the boat, you're looking at something weird, but at the same time, you're also looking at something predominantly iron, which looks like a meteorite, no matter what you do. Whether you find nickel or not, that you're looking at something that looks meteoritic in nature.
Exactly.
Yeah, but there is sort of within the question of interstellar objects, there is a sort of elephant in the room. And it's one of the most ultimate elephants in the room in the universe, supernovas, shooting out weird metallic composition stuff, and possibly some of it at very high speed. So, what differentiates this that would lead you to suspect that, well, maybe this isn't a meteorite fall. Rather, maybe we're finding supernova bullets, which there have been some indication, at least iron nuclei recovered off the ocean floor. And this is also why I asked about the control, is that if a supernova shot something at us that you could actually recover, it might look weird isotopically. So how do you try to differentiate that? Is it simply because the fragments that you're finding are within the search zone predicted for IM1 versus something that might be a broader type of deposit on the ocean floor?
Yeah, exactly. So we're paying close attention, and we will continue to pay close attention to the differences that we observe between the control region and the test region. Now, we already observed some differences in terms of bulk composition, including, yeah, differing ratios of magnesium and some other elements, and morphologies also seem to vary. But what's going to be key is, with the ICP-MS instruments that we have access to, we can analyze the full periodic table and do all of the isotope ratios that we could ever want. And those are very, very sensitive, and we can directly compare those to the known composition of the Earth and the solar system. Now, if there were fragments that came from a supernova, we might expect them to be enhanced in things like iron 60 and also in our process elements. And so that would be really, really exciting as well. But personally, I've been looking forward to this analysis for so long, because the isotopic ratios are the key in terms of establishing interstellar material. And if we are able to definitively establish that this came from outside of the solar system, if the isotope ratios are very different from what we find within the solar system and for material that has accreted onto the Earth, that would be truly historic. It would be the idea is that if you wanted to get material like this from the nearest star system, it would take at least several 100,000 years, the age of our species. That's the most optimistic estimate you can get with conventional rocketry. Nature, in a way, has already delivered this gift to our doorstep. And if we're able to determine that we truly found interstellar material, it would have taken us less than a decade. So that's an improvement by 4 orders of magnitude. it's really exciting because in a way it meshes geology with astrophysics. And it's a lot like if you think about the discovery of the first exoplanet. That was a new window into understanding our context and understanding how weird we are or how non weird we are relative to our neighbors. And the study of exoplanets, we went from one to over 5,000 now. The study of exoplanets has given us crucial information about our place in the universe and how unusual our home is. And this is really quite a similar window, and it also provides a new way of studying the stars, which is actually interacting with material from other stars, from either other planetary systems or supernovae or astrophysical phenomena in general. And I personally find that thrilling.
Oh, absolutely. If you have a supernova long ago depositing samples, physical samples of materials on your planet, which, I mean, in a way, all materials from our planet originate in supernova, but you get a different supernova and you can actually start studying what are the actual chemical differences that occur in a supernova between one next to another. And that's where this lack of nickel seems interesting to me. What's different? Why is this so low compared to solar system meteorites in general? But for those solar system meteorites that lack nickel on this level, then where did they come from? Are they interstellar objects? So do you see that we could re-examine based on the results of this, say it went in the supernova direction? Can we look at our meteorite collections and say, well, we have a new way to determine if some of these are interstellar that people have picked up over the last 500 years or whatever?
Oh, absolutely. Iron and nickel are usually produced together, but we see in meteoritic fragments that there's a huge range of the nickel content, and that could be due to actually reflecting the amount of nickel in the progenitor, or it could be due to nickel evaporating during descent, and that being a function of speed or other parameters. I think what's going to be key is testing these isotope ratios of iron and chromium, and especially if we end up confirming that we found pieces of interstellar material by studying the isotope ratios and determining them to be across the board anomalous. I think that will motivate reanalysis of previously recovered meteoritic fragments using those same tests, running ICP-MS and checking these very high precision measurements of iron, chromium, and many other elements' isotope ratios. That may yield many, many more discoveries.
Now, any indications, and this has been the overarching question in the media, is so far, any indications of artificiality? In other words, could these samples be representative of perhaps a piece of technology or whatever process? But is there anything there so far that looks a little bit artificial?
I don't think there's anything so far that implies an artificial origin. I would say that the big unusual thing about IM1 was the fact that it was extremely tough. It burned up low in the atmosphere and at a high speed. And so that means that the ram pressure at breakup was very high. And in fact, it was around 200 megapascals, which is much higher than observed for solar system meteors. But that doesn't necessarily mean that it's artificial. It just implies that perhaps meteors and other solar systems could have different strengths, or it might not even be from a solar system. It could be from a supernova or another astrophysical phenomenon, but that doesn't necessarily imply an artificial origin. And so far, the things that we found in the spherules, iron, magnesium, chromium, titanium, none of them imply artificial origins. I mean, there were a couple of fragments that we found that looked more anomalous, but were consistent with, they had things like rubidium and other unusual elements in them, but they were consistent with a burned up solar panel, let's say from a satellite or burned up semiconductor or something, and they were very different from the composition of the spherules, and it looked like basically burnt up human technology like a photovoltaic array. But in terms of the spherules themselves, I think the key question is confirming whether they're interstellar or not, because they certainly are, extremely interesting samples. And if we find that they're for sure interstellar, or any of them are for sure interstellar, that's a historic discovery. No indications of artificial origins, though.
Now, the promise of finding a main mass. After going through the dragging the sled, and based on particle size, do you think that you're somewhat close to actually finding where the main mass, if there is one, or main masses, that would solve even more problems than spherules would? Do you think you're close? Do you think it's worth going back out there and looking in even more specific areas based on the distribution of the particles and their sizes?
Yeah, well, I think that it depends on the composition that we end up finding. Whatever spherules, if we find spherules that have very distinct isotopic signatures from our search region that imply that they're interstellar, then we could study those compositions and understand that if you had a parent body composed from those elements and those isotopes in the ratios that were observed, what would burn up look like? We can actually model in detail using the light curve and composition data and seismic data. We can paint a comprehensive picture of the breakup of IM1 and the burnup in the atmosphere. And I think that will be key in telling us if we should expect anything other than molten sub-millimeter spherules, if we should expect some mass to survive or not. But yeah, I think that ends up depending on the composition.
Any indication so far from the composition to say that this seems to match the actual tensile strength of IM1 that came in? In other words, are the spherules, do they appear to be hard enough to fit the bill for this object based on what the satellite saw?
Yeah, so it's a little bit difficult to tell from fragments, especially melted fragments. So, to put it in context, when we observe iron meteors and collect meteorites from their falls, you might observe a meteor breaking up at a ram pressure of, say, 50 megapascals, and then you collect the iron meteorites and you test their strength, their tensile strength, and you find that it's actually something more like 400 or 500 megapascals. And so there's this trend of the measured tensile strength of fragments being between a few and an order of magnitude different from the observed ram pressure at breakup. And in a way that makes sense, right? Because if those pieces could have been broken up at 50 megapascals, they would have been, and they wouldn't have survived. But then when you talk about melted material, it becomes even more fraught, because a lot of the things that go into the strength of a meteor have to do with macroscopic structure rather than and those get erased when you completely melt something and mix it with air and create oxides and different structures, etc. So we will be looking into it, and also looking into recreating these alloys in the laboratory, but it's very, very difficult to tell, to basically match the tensile strength of a fragment to the observed strength in the atmosphere, because they're usually off by a factor of 3 to 10.
There is a whole lot of physics going on here, from the birth of whatever the object was in a supernova or whatever to its fall into a planetary atmosphere, and then its analysis. I definitely don't envy having to work that process out, but at the same time, that's very important, because that tells you, you would learn more about interstellar objects and the physics of them just from a spheral than the entirety of modern astronomy has ever learned about anything like this. So it seems to me to be probably a really fruitful and worthwhile thing to try to find other examples to compare to IM1. And by that I mean IM2. Is there any progress as far as going and looking for IM2, which is a completely separate fall, a completely separate potential object of artificial origin that may have even been larger than IM1?
Yeah, I I consider IM2 to be my second child, if you will, but in some ways even more exciting than IM1 because IM2 actually came in at a slower speed, meaning that there's a higher chance of finding larger fragments, and it was about 8 times more massive. So those two factors combined means that there's a higher chance of success and there's a higher chance of finding chunks of interstellar material. And so IM2 is really top of mind for me. It burned up off the coast of Portugal in March of 2017, and we're currently awaiting government confirmation on the data related to IM2 in a similar way that we were waiting for IM1. But I'm very excited about searching for fragments from IM2 and getting our hands on either the first interstellar material, if these spherules don't pan out, or bigger chunks of interstellar material and perhaps unmelted fragments.
Now, timeframes as far as the analysis of IM1, when can we reasonably start expecting some results from the testing that's going on at Harvard and I believe one other institution on the West Coast? When you guys look at this material, how quickly can you publish?
Yeah, we're expecting to have a initial read within a few weeks. So the good news is this analysis, at least, the first pass can be done relatively quickly. So we're hoping to know more very soon. Of course, what makes it a little bit longer than instantaneous is the fact that these data have to be very carefully calibrated and corrected for potential interferences between different isotopes that have the same atomic mass and other effects. But the bottom line is we're hoping to know a lot more within a few weeks, and the detailed analysis will continue for likely many months after that. So it'll depend honestly on what we know within a few weeks and what looks promising and what looks mundane. So I'll keep you posted.
Future expeditions, does it look good? I mean, given this produced results, I mean, there's materials to study, so it was fruitful one way or another. Future expeditions to recover more of IM1 and also IM2. So what's that look like? I mean, does it look like this is going to be an ongoing? Will there be another expedition? Let me put it that way.
Yes, definitely. An IM1 expedition will be dependent, of course, on the results of this one, and IM2 is dependent on confirmation from the government. But absolutely, the question is the answer is yes, and it all depends on these things that we're waiting for. And then the good news is that we've done it once, and so we learned a lot from searching for fragments of IM1, and so in the future it won't take as much sort of lead up time and preparation because we have established procedures.
My final question for you is a simple nuts and bolts question. So what's the sled look like after after all of this? Could you actually reuse that thing, or is it pretty much done for?
Yeah, it's actually in very good shape, and we have, I think, 2 spares. So these sleds were really, really hardy. And in fact, one of the things that we're going to be doing is reviewing video footage from the cameras attached to the sled, because even from a quick scan, we saw that there was a lot of stuff on the ocean floor that the sleds would run into, but they certainly held their own. And the one that we used the most ended up in very good condition. So we are really grateful. I'm just really grateful for all the people who made this expedition actually happen, because without the brilliant team of engineers, without the crew on the boat, without all of the people involved to make these logistics happen, to fund this expedition, I mean, every piece of the puzzle came together beautifully, and it wouldn't have if even one link were weak. And so at the end of the day, all of this science, all of this exciting science is really made possible thanks to the men and women who actually built these instruments and enabled the science.
How many people were involved? I mean, if you had to come up with an aggregate total of how many scientists, engineers, and personnel specialists, everything, how many people were involved in this expedition, would you estimate?
Well, on the boat, about 30, but in total, involved in the expedition, I mean, that's definitely north of 100. So it really takes a village. It really takes a village to search for and potentially retrieve humanity's first confirmed piece of an interstellar meteor.
Well, this was unbelievably fascinating from the very beginning, which we talked about. We've been talking about this for years. And then it came to fruition and, an actual expedition, and it came back with results. Do you feel after all of this time from sitting there doing the calculations and sitting there in a dorm to now, do you feel that this was just particularly special in your career? A good way to kick it off, as it were?
Oh, yeah. I mean, I started working in the field of interstellar objects right after the first one was discovered. And in the 6 years that the field has been alive since the detection of Oumuamua, it's really become a new field and window into astronomy. And the holy grail, of course, is actually finding and physically studying interstellar material. This process has been a dream, from finding IM1 in a publicly accessible government database to confirmation to dreaming up this ocean expedition to it actually happening and us having candidate potential material. I'm just really, really grateful to everyone who has enabled this science, and that includes credit where credit's due. That includes the government. I'm very grateful for the vision of the people within the White House and the DoD for collaborating with the scientific community and actually confirming the veracity of their measurements, and that was crucial in terms of enabling this potential study of interstellar materials. So this has been immensely gratifying, incredibly exciting. It's been a round the world adventure, literally, and I can barely sleep waiting for the results of the analyses that we have going on right now, because I really want to know what we found.
All right, Amir, congratulations. I'm very happy. I'm particularly that you're always taking a shot in the dark when you do an expedition like this. Maybe you wouldn't have found anything, but you did, and we have something to study, and I find that particularly fascinating. Next time we talk, I want to get into the idea of finding interstellar objects in space that the solar system has captured. But until then, I wish you great luck, and I hope that you'll keep us updated as to the analysis of these objects.
Absolutely. Yeah, looking forward to it.
Anna, I'm so glad we decided to attend this sci-fi convention the Possum recommended. I love sci-fi conventions. What I'm confused about, though, is the part about a potluck dinner. I spent 7 hours last night making these cookies. I really hope people like them. I think they will.
Hold on, John. I'm driving.
I wonder
John,
what...
I'm driving. Hold on.
Oh, yeah, automated driving. I forgot. Yeah, it doesn't yet work well. So what sort of cameras
John,
do you...
I'm doing 4 kilometers per hour. In zero traffic, John. Oh, you have reached your destination.
Well, sure is nice in here. Look, they have curtains. Wait a minute. There's nothing in here except possums. It's a possum convention, and one of them is dressed as a Klingon.
Yes, John. It's the annual Opossum Science Fiction Convention. You've won Human of the Year.
Well, that's nice. What was it for? My sci-fi books?
No, John, just Human of the Year.
All right. Well, I guess I'll put the cookies out here on the potluck table. Wait a minute. Sprocket is the judge. He's holding a gavel. Wait a minute. He just judged without sampling my cookies.
Oh, my cesium-free kale casserole.
Yeah, hold on. He just gave himself first prize for his famous pine cone salad à l'orange.
His what?
Yeah, no, look at these entries. Bone and neutron stew, weeds with leeks, and beak scones, whatever that is. Wait a minute. This whole thing was rigged.